Okay, good morning all of you. So let's get started where we left yesterday. Any questions before that? Any questions? Anyway, let's get started.
Okay, let me just mention a few sentences. See, this is the first time you are seeing a nonlinear material behavior, and hence the importance of the stress strain curve you should realize. In the analysis, first we are drawing the strain diagram, and from that we are plotting the stress across the depth. Whatever stress strain diagram we are idealizing, that is being mapped across the depth. And hence, this is the most important aspect of this analysis at ultimate state. Okay.
Anyway, you need to look at your IS 456, page 64. Once again, let me briefly summarize what we did yesterday. We looked in detail the stress strain curve for concrete. And once again, we try to understand what are these three curves here. And the lowest one or the bottommost one is the curve, that is the design curve that we'll be adopting for our analysis as well as design of a section as per IS 6. And salient points on this curve, you need to make a note of it. The curve is going to start at 0 strain value and is going to have a parabolic variation till strain value is 0.002, and thereafter the stress is going to remain at 0.67 FCK divided by gamma m, which is going to be 1.5. So 0.67 divided by 1.5, it turns out to be 0.447 FCK. Okay. And the distance, one more thing, the distance from 0 strain value, the ratio of distance from 0 strain value to strain value of 0.202 to the distance from 0 to 0.2035. That distance you need to make a note of it. That distance is going to be 4/7. And the distance between the strain values of 0.20, okay, that distance in terms of the ratio 0 from distance from 0 strain to 0.002 divided by distance from 0 to 0.0035, that turns out to be 4/7. And also the distance between 0.202 to 0.2035, the distance between that to the distance between 0 to 0.2035 turns out to be 3/7. That those two ratios you need to keep in mind. Okay. And one more thing is this: once you have this stress strain curve for concrete, and if you see the stress distribution or for a given section, or stress block for a given section is going to look like this figure 22. So it's basically rotating this stress strain curve by 90 degrees. Okay. And also this two more points. Maximum strain in concrete at the outermost compression fiber is taken as 0.2035. So the maximum strain in concrete in the outermost compression fiber under flexure, under bending, as per IS 456, it's limited to 0.2035. And also the maximum strain in tension reinforcement in the section at failure shall not be less than 0.87 Fy divided by ES or Fy divided by 1.15 ES plus 0.202. What is this 0.202? It is nothing but it's coming from the definition of proof stress. okay, or it's coming from the definition of 2%, the stress corresponding to 2% strain, okay. So the maximum strain in tension reinforcement should be greater than this value. Based on these two assumptions, yesterday we have, anyway, these whatever we just discussed, they are given in these figures. Stress strain curve for concrete, stress strain curve for steel, and a rectangular section is taken for illustration purpose. Rectangular section having dimensions B and D, reinforced on the tension side. Area of the steel is the tension reinforcement. Area of steel in tension reinforcement is AST, and the strain distribution or strain diagram is based on the assumptions, the strain, and also based on the assumption that plane sections remain plane before and after bending. Strain diagram is drawn, strain distribution diagram. The extreme fiber in compression in concrete, strain is limited to 0.2035 and having a linear variation with the zero strain at the neutral axis, and the strain at the tension, strain at the level of tension reinforcement is ES. ES is actually greater than 0.87 Fy divided by ES plus 0.202. Okay, once you get the strain diagram, you can make use of this stress strain curve for concrete and get this stress diagram. So strain is varying from 0 here to 0.2035. At some point it's going to be 0.202. So the stress distribution diagram is going to be linear. It's going to be it's going to be parabolic from 0 strain to strain of 0.202, and thereafter it's going to have a straight line till 0.2035. And the maximum stress value, the stress value is 0.67 FCK divided by gamma m, which turns out to be 0.447 FCK, or if you round it off to the second significant digits, it is going to be 0.45 FCK. Okay, and here this compression zone or compression, this stress distribution in compression is going to have a combination of rectangular and a parabolic portions. So the resultant compressive force, the value is turns out to be 0.36 FCK XU times B, and how this is obtained we'll see in a while. Okay, this is where we stopped yesterday. And also the resultant compressive force is going to act from the top, it's going to act at a distance 0.42 XU. XU is nothing but neutral axis depth. And once this is 0.42 XU, the lever up, that is the distance between the resultant compressive force and the resultant tensile force, it's going to be effective depth minus 0.42 XU. And what about tensile force? Tensile force is straightforward, because if you see the stress strain diagram for steel, any strain exceeding this value 0.87 Fy divided by ES plus 0.202, stress value is 0.87 Fy. So stress or the tensile force is stress in steel 0.87 Fy multiplied by area of steel. Okay. So our focus of today's class is to understand, or one of the point that we need to understand is how this 0.42 is obtained, or we need to cross check whether this 0.42 is correct or not, 0.42 times XU, and also whether this resultant compressive force turns out to be 0.36 FCK XU times B. We are going to cross check these things. And before that, here this area can be split into a rectangle and a parabola. So we need to make a note of, it's not actually parabola, it's going to be semi-parabolic in shape. So we need to make a note of how to find area of such kind of shape, and also where the center of CG of that particular type of area is how to calculate that, where it's going to lie along horizontal axis as well as vertical axis. So that is where I stopped yesterday after showing you. So you take a note of this if you have not done it. Semi-parabolic, and these are all well documented. I have just taken it from Wikipedia. So this is the semi-parabolic shape. And if this dimension is A, if this dimension is A and this dimension is H, and where the CG is going to locate along the horizontal axis, 3A divided by 8, and where CG is going to locate for this semi-parabolic area along the vertical axis from the bottom, it's 3H divided by 5, and area of this semi-parabolic shape is 2AH divided by 3. So please take a note of it, because we are going to make at least we don't require this 3A divided by 8, but we require what is this 3H divided by 5 and 2AH divided by 3. Okay, please take a note of it. Okay, 3A divided by 8, CG location, CG location along the vertical axis, 3H divided by 5, and the area is 2AH divided by 3. So let's, just now we have seen this one, but if you, this is showing as a plane, stress distribution is shown as a plane diagram here, but if you see the 3D view of it, it's going to look like this. 3D view of that stress distribution is going to look like this. Okay, take a note of this one. And here everything is given up to 3 significant digits. And whatever quantities, the ratios of the distance on the stress strain curve that I mentioned, 4 divided by 7, 3 divided by 7. Based on that, if the neutral axis depth is XU, starting from 0 strain, and the rectangular distribution take a note of it. Any questions here at this stage? Please make sure that everything is clear to you. Okay, if you have any questions, please raise those things at this stage. And one more request, I think now student strength is increased. Please don't start recording from your end. Okay, that is what is causing the problem. So take a note of this figure quickly if you have not done it. And suppose once it's very, please note that video is not going to be continuous if you do this kind of thing. Okay. Please don't start recording from your end. So please take a note of this figure. And there is a mistake here. That's why this is striked out. This is striked out. It is actually TU is nothing but you can say ultimate tensile force, ultimate compressive force, or if you want, you can drop out this subscript. You can just say T. T is the resultant tensile force, which is going to be 0.87 Fy times area of steel, and resultant compressive force is 0.362 FCK XUB. So as I mentioned, we are going to understand how this quantity, this resultant compressive force, whether this is correct or not, we'll try to understand that, as well as the location where this resultant compressive force is acting from the top fiber, which is going to be 0.416 XU. Any questions? So if there are no questions, and this figure is important, okay, you please take a note of this figure, and then we'll go further. So before we go further, let's understand with this figure here. Okay, so this rectangle, this combination of parabolic portion as well as this rectangular portion, we are going to split it into parabolic portion and rectangular portion separately, and we are going to find the total compressive force because of this parabolic region. What is going to be the total compressive force because of parabolic region? I told you to make a note of the area of that semi-parabola shape. Area is given by 2. The formula that you noted is 2AH divided by 3. So here, what is 2? What is A? A is nothing but point. Please take a note on your paper, okay? 2 times 0.447 FCK, 2 times 0.447 FCK times 4 divided by 7 XU divided by 3. That is going to be area of this parabolic shape, semi-parabolic shape, and this stress is acting over a width of B. So total compressive force contribution from this parabolic, semi-parabolic region is going to be, once again I'm going to repeat, 2 times 0.447 FCK times 4 divided by 7 XU divided by 3 times B. Please take a note of it. And similarly, the compressive force contribution from this rectangular region is going to be, it's straightforward. It's going to be 0.447 FCK times 3 divided by 7 XU, 3 divided by 7 XU multiplied by B. Do you agree? And where the compressive force contribution from rectangle region is going to act from the top. From the top, where it's going to act? It's going to act at half of 3 divided by 7 XU. And where the compressive force, for this semi-parabolic, compressive force contribution from this semi-parabolic region is going to act. I told you to make a note of this CG location here. Y bar is 3H divided by 5 from the bottom of this semi-parabolic region. And if you want from the top, it's going to be 2H divided by 5. Okay? 2H divided by 5 from the top of the parabolic, semi-parabolic region. So, the resultant compressive force from this semi-parabolic region, at what distance it's going to act from the top fiber? It's going to be at a distance 3 divided by 7 XU, 3 divided by 7 XU plus 2 by 5 times 4 by 7 XU. Okay? And how do we get the resultant compressive force? And where the location, where this location where this resultant compressive force is going to act? you need to do making use of these two contributions from parabolic region as well as rectangular region. You need to do some manipulation and get the resultant compressive force as well as the location where it's going to act. All those details are given here. So let's make a note of it. That's why I told you to make a note of that figure. Okay. Anyway, we already noted, you agreed with me, this semi-parabolic portion region, that the length over which it's going to act is given by 4 divided by 7 XU, and the depth of the rectangular portion of stress block, it is 3 divided by 7 XU. So these two quantities are noted. And area of rectangle, area of parabolic region, and if you add them together, you are going to get this 0.36 FCK XU. Please note that this is area of stress. If you want total compressive force, you need to multiply with the width as well. Here, total compressive force is area of stress block times width of the beam, which is B. That is 0.362 FCK XU times B. And total tensile force is straightforward. Stress in steel, which is 0.87 Fy times area of steel, AST. So any questions till this point? You need to make a note on your in your notebook, okay? And now where the centroid, or where the resultant compressive force is going to act from the top fiber. Here, the depth of the total compressive force acting at the CG of the stress block from the extreme fiber in compression, where it's going to act. It's going to act at a distance given by this. Compressive force contribution from rectangular region multiplied by the CG of the rectangular portion, compressive force contribution from parabolic, semi-parabolic portion multiplied by location of CG from the top fiber divided by total compressive force. So if you do this manipulation, that is how you get this 0.42 XU, or if you want up to 3 significant digits, it's going to be 0.416 XU. Is it clear? Professor Amlan, you want to add something here?
No, I think it is fine. It is just, the idea is that we are integrating over the curves and trying to find out the area and the centroid. Okay.
Anyway, these two quantities, this 0.36 FCK XU, that is area of this stress block, 0.36 up to second significant digit, 0.36 FCK XU, and this the location or the CG of the resultant compressive force 0.42 XU. They are given in the code book under note. They are directly given in code book under the notes, under this note. Okay. Why they are given here? Because this entire thing is coming based on whatever stress strain curve IS is specifying us to use. If the stress strain curve is like this, a combination of parabolic portion, rectangular portion, then the area of stress block is given by this. Okay, and please note that there is no empirical kind of relation here. Everything is you can derive it from mechanics. Okay, so if this is clear, then we can actually start writing the moment of resistance and other things. Okay, and before that we need to find the neutral, this XU. How to get this XU? How to get the neutral axis depth? And if you go back to whatever you have done, how did you find the neutral axis depth? Neutral axis depth you found, so far what you did is you found by equating moment of area in compression about neutral axis to moment of area in tension about neutral axis. Okay, moment of area in compression neutral axis to moment of area in tension.
No, this way.
Moment of area in tension.
Yeah, this way it is for the working stress method.
Yeah, just wait a minute. That's okay. What I just want to remind that. Okay. Okay. So far, what you did is this one, equating moment of area in compression to moment of area in tension. But there is another way of finding it. If you want this section to be in equilibrium, section to be in equilibrium, resultant compressive force should be equal to the resultant tensile force. Now, since based on the strain diagram, we know the extreme fiber strain, which is limited to 0.2035, and also we once we have the strain diagram, we can find the stress diagram. And also by the time we have a section with us, or even if we are designing, we know what is the grade of concrete we want to use. So we have the entire stress distribution here. Once the grade of concrete is known, I can draw this. I can get the numerical values of everything except the neutral axis depth. And also once the grade of steel is fixed, I know what is this Fy. So I also know what is this 0.87 Fy, and if I know the area of steel, I can find, if it is analysis kind of question, if area of steel is given, I can find the total tensile force. So only unknown is neutral axis depth. So here what we are going to do is we are going to equate total compressive force to total tensile force. This is based on the equilibrium. Okay, equilibrium equation. Otherwise, section is not going to be in equilibrium. So total tensile force or total compressive force is equated to total tensile force. Just now we found what is resultant compressive force. Resultant compressive force is 0.362 FCK XU times width of the section, and total tensile force is stress in steel, which is 0.87 Fy times area of steel. Please take a note of this equation. From this equation, you can rearrange it and get the neutral axis depth. Please take a note of all these equations which are given here. Neutral axis depth can be obtained like this. And here 0.87 divided by 0.32, that it's calculated, and it is what is written here. Or if you want neutral axis depth, usually is expressed as a ratio of effective depth. So instead of writing XU, you can write it as XU divided by D and get this equation. And I hope you recognize what this is. This is nothing but percentage of tension steel. So neutral axis depth is going to depend on neutral axis, ratio, neutral axis depth ratio, you can say. Neutral axis depth ratio is going to depend on the type of steel or grade of steel, grade of concrete, and percentage of tensile steel. Once you get neutral axis depth, you can find the lever arm distance. Please take a note of all these equations. And if you have any questions, please raise it at this stage. Any questions? So everything is clear?
Yes, sir.
Tell me. Okay, so let's proceed. Now let me go here. Let's take this strain diagram. Let's consider the limiting case. Limiting case in the sense, we'll whatever codes assumptions are there. One of the assumption is maximum strain in compression in concrete at the outermost fiber, at the extreme fiber, under bending or flexure should be limited to 0.2035. The other assumption is maximum strain in tension reinforcement shall not be less than. So shall not be less than, some value is given, 0.87 Fy divided by ES plus 0.202. So let's assume exactly strain in steel is 0.87. It shall not be less than, but it can be, no. So let's assume strain in steel is 0.87 Fy divided by ES plus 0.202. So strain here is 0.87 Fy divided by ES plus 0.202, and strain here is 0.2035. Please note that strain in steel is going to be same as strain in concrete, because otherwise compatibility will not be there. So strain distribution diagram, it's going to be same whether with respect to concrete or steel. Okay. So now with that understanding, so you take this value as 0.87 Fy divided by ES plus 0.202. And from the properties of similar triangles, this strain value, what is this distance? XU divided by XU divided by, or XU, the ratio of XU to this distance is D minus XU. Ratio of XU to D minus XU is going to be in the ratio of 0.2035 to 0.87 Fy divided by ES plus 0.202. Is this clear? So you just take a note of this strain diagram, because for the next equation or next relation that we are going to note down, that information is required. Okay. So whatever I just mentioned, if you rearrange it, you are going to get that one here. Whatever I just mentioned, XU divided by D minus XU is going to be 0.2035 divided by this value, 0.87 Fy ES plus 0.202. And instead of XU, it is written as XU max. Why it is written as XU max? Because we are using the limiting values. We are using the limiting values of strain in concrete and strain in the steel. Any questions here? This equation, this relation is very, very important. And if you rearrange this equation, and just now we noted XU divided by D in terms of Fy, which is going to depend on grade of steel, FCK, which is going to depend on grade of concrete, and percentage of steel. That is neutral axis depth ratio I mentioned. But here it is same, neutral axis, it is also ratio, neutral axis depth ratio, but this is a limiting value. That's why it is written as XU max divided by D. And please note that this XU max divided by D is going to depend only on the grade of steel. You please take a note of this relation. So in your limit state method, once the grade of steel is given, you need to calculate XU max divided by D. And this is for limiting case. Limiting case is nothing for a balanced section. This is like a balanced section. Extreme fiber, the compressive, the strain in the extreme fiber in concrete under bending compression is limited to 0.2035, as well as maximum strain in tension reinforcement is equated to this value. It shall not be less than this value as per the code. We are equating it. That's why we got for a limiting case, which is for a balanced section. And given any other section, hope you have taken note of this one. Given any other section, you need to calculate XU divided by D using this relation and make a comparison. If your XU divided by D, please note that this is based on the, let's focus only analysis at this stage. Okay, let's assume you are given a section. And you know what is the grade of concrete, what is the grade of steel, and what is the amount of tension reinforcement that is provided. So then you can easily find what is this ratio. And this ratio, if you compare with this one, this depends on the, this is for a balanced section, this depends on the grade of steel. And if your XU divided by D is less than this, if XU divided by D is less than this value, then it's going to be under reinforced. If your XU divided by D is exactly going to be equal to this, then it's a balanced section. If your XU divided by D is greater than this, it's going to be over reinforced. And as per limit state method, over reinforced section is not recommended. Okay, you need to redesign the section. So now, if this is clear to you, are there any questions here? If this is clear to you, what is this XU max divided by D for different types of steels that is given in your IS code here? XU max divided by D for different grades of steel is given here. So your neutral axis depth, your XU max is nothing but limiting neutral axis depth for limiting case, which is for a balanced section. So if you want to find for a balanced section, what is the neutral axis depth? If you know the depth of the section, effective depth of the section, if you know the type of steel, you need to just multiply with this ratio, which is given in IS 456. And how these values are obtained? They are obtained from this relation. Substituting in this relation, substituting what is Fy corresponding to, if it is Fe415, what is Fy corresponding to that, or if it is any for any other steel, Fy corresponding to that, and modulus of elasticity of steel for even whatever grade of steel, it's going to remain same, 200 GPa. And based on that, you can calculate XU max divided by D. And that is how this is obtained. That is how these are given here. Any questions? No questions? Okay. And before we close for today, I'm going to give enough time for you to digest, okay? And in tomorrow's class, we'll see the other things. Before we close in, I want you to refer to Annexure G. I want you to refer to Annexure G of IS 456. Please note that whatever relations we noted, they are given in the code book. But before you make use of them, you need to understand how they are obtained. Okay. So let's read this. Moments of resistance for rectangular and T section or flanged sections. Okay. Moments, the moments of resistance of rectangular and T sections based on assumptions given 38.1. It's nothing but assumptions under limit state of collapse under friction. So for rectangular sections, that's what we looked at today. And sections without compression reinforcement, that is what we looked today. The moments of resistance of rectangular section without compression reinforcement should be obtained as follows. Determine the depth of the neutral axis from the following relation. This is what you noted. That's why I'm saying you need to make a note of it, or when I'm explaining, you need to make a note of it. Otherwise, when you see this equation, you may not understand where it is actually coming from. Okay, this is actually coming by equating total compressive force to total tensile force. Okay, so this is the relation we noted, and whatever I just mentioned, that is what is written here. If the value of XU divided by D given by this relation is less than the limiting value. What is the limiting value? XU max divided by D, note below 38.1. Let me go and show you what is this 38.1 for completeness. Here, this is 38.1, and note below 38.1 is just now whatever we have seen. XU max divided by D. So once you get XU divided by D, you need to compare with this value. So that's what Annexure G is saying. If the value of XU divided by D is less than the limiting value, if it is less than the limiting value, what I told you, what is the kind of section? You need to be interactive, understand? If XU divided by D is less than XU max divided by D, it's under reinforced section. If it is under reinforced section, steel is going to dictate the moment of resistance. How do we calculate moment of resistance with respect to steel? It's stress in steel multiplied by area of steel multiplied by the lever arm distance. So let's see whether that is what is this one. Stress in steel 0.87 Fy, area of tension steel AST multiplied by the lever arm. Is this the lever arm? Let's see that. Here. Lever arm is given by, just now we noted the resultant compressive force is going to act at a distance 0.416 XU from the top, from the extreme fiber in compression. So lever arm is given by effective depth minus 0.416 XU. And now XU is given by this. XU is this one. So you need to do small homework, or you need to just cross check. If I substitute XU is equal to this 0.87 Fy AST divided by 0.362 B times FCK, if I substitute that here, okay, and by taking that as a lever arm, whether I'm getting whatever is given in Annexure G or not, you please cross check whether this is correct or not. Okay. So you need to calculate XU divided by D and compare with limiting value of XU divided by D. And then if it is less than XU max divided by D, if XU divided by D for a given section is less than XU max divided by D, then it's going to be under reinforced. Please note that in this it's not mentioned whether it's under reinforced or something like that. Wording is not used. But here it's directly given moment of resistance is with respect to calculated with respect to steel. So that itself means it's under reinforced. Okay. So you please cross check whether this relation is correct or not, whatever is given in the code book, using whatever I showed you. And now let's go further. If the value of XU divided by D is equal to the limiting value, that means it's a balanced section. The moment of resistance is given by, you can calculate either with respect to steel or with respect to concrete. Here that relation is given with respect to concrete. That relation is with respect to concrete. What is just now we noted what is the total compressive force, resultant compressive force? What is that value? 0.362 FCK XU times B. And if you round it up 0.362 to second significant digit, it is 0.36. 0.36 FCK. FCK is there here. And 0.36 FCK XU times B. Okay, B is also there here. XU instead of, because this is a limiting case. Here XU is same as XU max. So instead of XU max is used. And it is actually written in terms of XU max divided by D, and you can check whether this relation is correct or not. How do you check whether this relation is correct or not? You resultant compressive force 0.362 FCK B FCK XU times B, that is the resultant compressive force. For limiting case, you substitute XU is equal to XU max, multiply with the lever arm distance. Lever arm distance we have seen how to calculate. You just substitute for limiting case XU is equal to XU max and cross check whether this relation is correct or not before you come for the next class. Okay, before you come for tomorrow's class, you need to cross check whether this moment of resistance is correct or not. Please note that here it is written with respect to compression, concrete. It is written with respect to concrete, but same relation you can write with respect to steel as well. A similar relation you can write with respect to steel as well. For a balanced section, whether you calculate moment of resistance with respect to concrete or with respect to steel, it should be same. Okay, anyway, think about it. And okay, we discussed if XU divided by D is less than the limiting value, if it is equal to the limiting value, and what about if it is greater than the limiting value? Then as per working stress method, it can be classified as over reinforced section, but here its over reinforced sections are not allowed. If XU divided by D is greater than the limiting value, the section should be redesigned. Okay, and all other quantities, the notation they are given here in the explanation. So I'll stop here. And if you have any questions, you can raise at this stage. And Professor Amlan, you want to make any comment at this stage?
Okay, let me just again emphasize the difference of finding out the depth of the neutral axis for the working stress and the limit states method. In the working stress, the stress was proportional to strain. And under that condition, the depth of the neutral axis can be found out based on equating the moment of areas of the concrete and the steel. But for the limit states method, the neutral axis is found out by the more fundamental condition the first equilibrium equation for flexural analysis, which is compression is equal to tension. We have to use this condition to find out the depth of the neutral axis for the limit states method. Okay.
Okay, please think about it. Okay, we'll discuss further if you have any questions. Just wait a minute. Okay, thank you.